So today I'd like to talk about learning, and I'd like to talk about human learning. I'd like to talk about classical machine learning, and finally I would like to talk about quantum machine learning. First, let's go all the way back and let's think about how humans learn. And in my opinion, there are sort of four main elements of human learning. First one is sort of the ground truth, the training data. The second one is the encoding. The third one is our brain or the neural network. And the fourth one is the optimizer. Let me go through all of this on an example. Let's say we are trying to learn how to name different fruits. How would this process work for a human? Well, there's this picture books that have images of fruits, and then attached to the image there's its name, and there might be a slider that you have to pull open to see what the fruit is called, right? This is sort of what's the ground truth or the training set. So it's somebody who knows what this fruit is wrote down its name. And this can also be like our parents, our teachers, our society. So somebody who was already able to recognize fruit, and they give us feedback. Right? Then we have the encoder. Encoder, it's essentially our eyes. And what they do is they take an image and they convert it into some electrical signals that our brain is able to process. So essentially going from whatever the base input is to something that our brain is able to process. Third, we have our brain. And our brain, the way it's structured, it's sort of, we have some neurons in here, and they're connected to each other through electric connections. Right? And they take the input, which was sort of pre-processed, encoded, and they give us the output, which is in this word, would just be the name of the fruit. And finally, we have the optimizer. And the optimizer for humans, this is just the feedback mechanism of we look at an image of an apple, we say this is an apple, we open the slider and it says an apple. And this makes us happy. Alternatively, we look at an image of an apple, we say this is a banana, we open the slider, we found out it was an apple, and this makes us sad. Right? What this does in our brain, essentially, it produces some chemicals that tie to these neurons. And then neurons, they start conducting electricity either better or worse, depending on if we guessed correctly. And in this way, we sort of transform the structure of our brain so that now we're able to recognize different fruits. Right? And essentially, I mean, you can think of this a little bit of our brain essentially as a function of different parameters. And then the happiness mechanism, it tries to optimize our brain so that this function achieves a minimum, right? I mean, this will make maybe a little bit more sense in classical machine learning. All right, so going to classical machine learning, the process is completely the same. We have the training data, we have the encoder, which just translates the training data into something that our neural network is able to process. Then we have a neural network, which is essentially artificial version of neurons that we have in our brain. And then finally, we have the optimizer. And the optimizer restructures the neural network so that it's in its minimum, or that it matches the training data as best as it can, right? And that's essentially all, right? So if we go to recognition of different fruits, for example, we would start with a set, we have images, we have names attached to images, and this is our training data. Then we have the encoder, where we translate the image into something that our neural network can process. For example, pixels or RGB or a binary representation or something similar, right? Then we have the neural network, which is essentially artificial neurons, and you can think about these neural networks essentially as a big function that depends on some parameters. And then we have the optimizer, right? So neural network gives an output, we compare it to the output that's expected. If it's good, reinforce. If it's not good, change and try different connections, right? And this is essentially how classical machines learn, right? So we turn this neural network into something that's now able to recognize different images of different fruits. Going to quantum computing, right? What changes? Well, not much. So conceptually, at least, the process is very similar. We still have the training data, we still have the encoder, we still have the neural network, and we still have the optimizer. Training data is essentially the same as for classical computer. Encoder, well, of course, we have to encode our data differently because we are not operating with bits anymore, we're operating with quantum bits. So what we have to do is we have to translate the data that we're giving into quantum bits so that the quantum neural network can process it. This can be challenging, and it can be challenging especially computationally. So this can take some time. And it's great. I mean, sometimes we're working with data sets which are already quantum, like from some measurements, from some experiments. Excellent, but otherwise we still have to do this encoding. And this can take some time. Then we have the neural network part. What's the neural network part in quantum machine learning? Well, it's something that we call a variational quantum circuit. And it's essentially a set of operations on quantum bits which depend on parameters. And we made this analogy before that a neural network or even our brain is just a big function that depends on some parameters. You can think of this quantum neural network for now, if you're not familiar with the subject, it's a function that takes quantum bits and gives output, which depends on some parameters, right? And this can be a complicated function, very complicated function, but it depends on some parameters. Typically, these are some rotational angles, so nothing even that crazy, right? And then there's some entanglement gates and so on, but essentially it's a function that depends on parameters. And then we have the optimizer, which tries to find the parameters so that the outputs will match the best the training data or the universal truth. And this optimizer, it typically runs it always runs essentially on a classical computer. So here it is. Here's the structure, right? You need the universal truth so that you even know what you're learning. You need the encoder for classical. This is a classical encoder. For quantum, you have to encode it in a quantum way. Then you have the neural network. In classical computers, you have the artificial neurons that we have in our brain. In quantum, we have a parameterized quantum circuit. Both are essentially a function that depends on a lot of parameters. And they give the output. And then you have the optimizer, which tells you how to change the parameters so that the output matches what you expect the output to be. Now for quantum machine learning, we are, of course, quite constrained. And we are constrained in how large this parameterized quantum circuits can be, and also how many operations we can do, because we don't want too large errors, and we are constrained by the number of qubits. So typically still in quantum systems that we would design for real life use, we would include some classical layers. So the systems for quantum machine learning are typically still hybrid in a sense that they still have some classical layers and then they have some quantum layers once we reduce the dimensionality sort of of the input data. And this is how we get the results. Yeah.